Welcome students. Now that we've completed the very first module in the basics of statistics, we'll take what we've learned, so constructs such as measures of central tendency and measures of variability, and now we'll apply them to statistical tests. So we'll learn several statistical tests throughout this semester. This very first one is what we call z-scores. And with z-scores we compare individual scores to overall populations. We can also compare individual scores from different populations. And so we'll take what we've learned about variability, measure of central tendency, and we'll start making meaningful comparisons that we can use to make real-life decisions. Before we can start making those comparisons, we need to talk a little bit more about the normal distribution, and from there that'll naturally lead us into z-scores. So z-scores are what we're really looking for in this particular module, that if we can calculate z-scores for any individual, we can compare them to the overall population. We can also compare them to individuals from other populations. But before we get there, let's talk about the normal distribution first. Now, if you remember from Module 1, we talked about the normal distribution. The normal distribution is a theoretical distribution. That means it doesn't really exist, but it does a really good job of modeling the world that we live in and the variables that we measure in our reality. And so the normal distribution, again, is a bell-shaped distribution. It's symmetrical and it's unimodal. In other words, it has one particular high point, or what we call one mode. In the center of our distribution, we have our measures of central tendency. In a perfectly normal distribution, the mean, the median, the mode will all be in exactly the same place. Now, in reality, we won't actually have a truly normal distribution. And so we always want to know, is our distribution normal enough given the data that we collect? And so if it is, then we can assume the normal distribution and we can create our calculations or conduct our calculations based on that theoretical distribution. If we have a mean and a standard deviation, so in other words a measure of central tendency, in particular the mean, and a measure of variability, in particular the standard deviation, then we can estimate the normal distribution of the data. And so when we say estimate, again, we're not saying that in the population that our variable is normally distributed. We're just saying from the data we collected, we can determine that the distribution in the population is normal enough. So that's why it's important that we conduct our skewness statistic that we learned in Module 1 to determine if the data that we have, the observed variables that we have, if they are normal enough for us to continue with our statistical tests. If it's not, we need to make corrections, and you learn those corrections in Module 1. So the example we used in Module 1 is communication major salary a year after graduation. And we said the mean was 42,500 and the standard deviation was 6,700. And so if we have those two numbers, the mean and standard deviation, then we can estimate the normal distribution. We can model the normal distribution based on those data that we collect. Now again, it's an estimate. It's not exactly what it is in the population. And so our estimate is what we call probabilistic to the population. So statistics is based on probability, and so when we estimate this normal distribution, there's a chance that it's not normally distributed. So it's probabilistic. Chances are when we make this model that it is close enough to normal distribution, but we don't know that for sure, and so it's what we call probabilistic. There's a chance that it's not normally distributed. And we can see that here, that the estimated normal distribution that we calculated from the mean and the standard deviation, which is the orange line, the bell-shaped line in this particular slide, doesn't overlap exactly with the actual data we collected for the 2005 communication majors. So the frequency polygon for the actual data for 2005 communication majors is the blue line. And so you'll note that it doesn't perfectly overlap. And that's okay because we're using an estimate. And if we can estimate this normal distribution, then we can apply our formulas for our statistical tests. If we had to use the actual data that we collected, then our formulas for our statistical tests would be very cumbersome. They'd be very difficult to calculate. And so we can make it simpler and make it easier to comprehend, again, by applying this estimate of the normal distribution. Okay. So what if, instead of using dollars, we relabeled our estimated normal distribution in terms of standard deviations? So we're going to change the unit of measurement from dollars, which we originally collected, and we're going to change it in terms of standard deviations. Now when we relabel in terms of standard deviations, we will no longer have dollars, but rather we'll have standard deviations. And so instead of adding and subtracting 6,700, we'll be adding and subtracting in terms of standard deviations. Once we have relabeled in terms of standard deviations, you'll notice that our normal distribution graph here no longer has dollar signs on it, because we've now changed the unit of measurement. So you'll notice that in the very center, this is where the mean would be, that there is 0 deviations from that mean. And so we center it about the mean, and at that point we say there are 0 standard deviations. In other words, the values don't deviate from the mean. So when we have 0 standard deviations, then we say that is the mean of our raw data, and our raw data was in terms of dollars. So the mean was 42,500, and we'll place that with 0 standard deviations. Alright, once we have that center, the mean relabeled to 0 standard deviations, then we can add and subtract a standard deviation. So if we go in the positive direction from the mean, from the middle part of our graph, then we can add 1 standard deviation, 2 standard deviations, and 3 standard deviations. You note that the further we get away from the center, the less frequent the observations become. And so we can continue adding standard deviations all the way to positive infinity. We can also subtract standard deviations in the negative direction from that mean or that middle point. And so we can have -1 standard deviations or -2 standard deviations, which is essentially saying that we're 2 standard deviations below the mean. And we can continue that for infinity, because remember that the normal distribution never touches the x-axis, so it extends for infinity in both directions of the mean, in the positive direction and the negative direction. Now once we've relabeled in terms of standard deviations, we have now standardized our measure to the standard deviations of the population. So we've taken our normal distribution, it's now in terms of standard deviations rather than in terms of dollars or in terms of miles or in terms of self-esteem scores or in terms of number of shoes in your closet, whatever it may be, and we've changed it to a standard unit of measurement called the standard deviation. Now once we do that, we have created z-scores. And so z-scores are standard scores. They're scores in terms of standard deviations. And once we have z-scores, we can now compare individuals to the overall population, and we can also compare individuals across populations. So if each population, we take our measurement and we change it to a z-score, then we can directly compare apples to oranges, so 2 different units of measurement that are unrelated. So something like self-esteem scores to how far students live from campus. Something that's not directly comparable by itself, but once we turn to standard scores or z-scores, we can now compare across populations.